Hello and good afternoon friends, welcome to the CEC-UGC live lecture. Dear friends, we have been talking on wireless multimedia networking since our two sessions. Today also we would be talking on wireless multimedia networking. We would be starting from the point where we left in the previous session. And for this very discussion, we have once again with us in our studios Dr. Advitya Sinha. Dr. Advitya Sinha is assistant professor in one of the leading institutions. So we believe that her experience would definitely help us in understanding the topic that is wireless multimedia networking. So let's welcome our guest, Dr. Advitya Sinha, and let's try to understand more and more through her. Hello ma'am, welcome to the lecture.
Thank you. Hello everyone. In this third series of lecture on multimedia networking, we will be mostly focusing on discussion about the traffic models and the energy management. In the last lecture, what we were discussing about was different ways of enhancing channel capacity, that is, the number of users that a particular cell can support. Because the number of users, that is the number of demand, can be increasing with time, and as the number of users increase or the devices increase in that particular region. Okay. In that concern, we addressed three important methods. The first was power control, that is, we can control the transmission power levels and the transmitters and the receivers, they should have the flexibility of choosing whichever level out of those, say, n subdivision of transmission levels that can be taken to flawlessly transmit the respective communication that is required. Now, the second one was cell splitting, and the other was cell sectoring. Now, just to have a short recap of what cell sectoring was. In fact, cell sectoring and cell splitting, these are very much widely used in support with zoning. Obviously, zoning is another method that we'll be studying shortly. Now, in cell sectoring, what happens? The cell is divided into sectors depending upon angles. We also studied differences between, list of differences between the sectoring and splitting. So what happened in splitting, that we don't divide into direction angles, but what we did, we subdivided the cell into further smaller cells. Okay. So in splitting, the radius of the homogeneous radius that we took R, it is subdivided into smaller value, so that now one particular cell can have a number of particular number of cells within a macro cell would tend to increase. Okay. So this would give rise to a number of picocells and microcells from the macro cells, obviously. Okay. Now, in this, the problem that the network administrators faced was in cell splitting, the number of base station antennas installed in each cells increase naturally, because the number of cells are now increasing as we have decreased the parameter R. So as the number of cells increase, the number of base stations increase, because remember that in each cell, according to the property of cell splitting, what happens, there is an individual base station associated. So as the cells increase, number of base station increases, and base station increases, it means that installation complexity increases, and also the maintenance part has to be more complicated. Okay. And one more thing that was one more problem that was associated with this cell splitting is that number of handoffs also increased a lot, because the boundary of the cells are now become very small. So there is a good tendency that a vehicle that is in motion can easily cross the cell boundary of one to another, resulting in frequent handoffs. Mostly these handoffs are unnecessary. But whenever a handoff is taking place, it has to be detected and managed, and all sort of allocation and deallocation processes has to be triggered. So for this particular drawback, what happened, prefer to switch, the network administrator preferred to stick to some other methods, one of which was cell sectoring. In this, the a particular cell was divided into sectors on the basis of angles. Now, these angles or direction angles, if they are equal, say if we have a 60-degree throughout, then we can say that it's a homogeneous cell. Or we can have a subdivision of different angles, different direction angles. In that case, it would become a heterogeneous sectors or heterogeneous cell sectoring. In heterogeneous cell sectoring or whatever homogeneous cell sectoring, this sectoring usually supports the concept of one base station per cell. Okay, so now we have one base station, which is unlike the cell splitting part, where we have many number of base stations depending upon how many number of macro and pico cells we have. Okay, so here that problem is resolved. And what else? For each sector we are allocated a transceiver. Okay, and this transceiver is often directional transceiver, because if they are not directional, that is, they do not focus in a particular direction, their coverage area, then what will happen? Co-channel interface problem will be there. So just to alleviate this problem of interference, the directional antennas were being used. Now, microcell zoning is another way of enhancing channel capacity that we will take up in the beginning of this lecture, and this will be followed by traffic management issues. We'll study on-off traffic model. It's a very basic model. It's based on Markov property of having different states and properties involving the state transitions, probabilities associated with each transition, etc. Then we'll take up the calling rates, how to find out the calling rates in traffic models, and the properties, the characteristics and challenges of multi-hop communication, and how a particular traffic model can be applied when a scenario like multi-hop communication is given to us. Because when we are talking about wireless multimedia, so these are handheld mobile devices, and the mobility rate depends upon where that person is traveling. It can be a vehicular communication, which is a high-speed communication, or it might be slight mobility, or even stationary. Okay, so depending upon that, multi-hop communication is very, very essential. So impact of traffic on different scenarios of multi-hop communication is important to address. Now we have, then we'll do the analysis part, analysis on different network parameters, the expected distance, expected progress distance towards the direction of target node, then the expected transmission time, so that we can analyze how much delay is incurred in communication. And then we'll start knowing about energy consumption management and how to harvest it from the nature or other sources, so that these devices can operate in a normal way, irrespective of if there is a large number of communication or whatever data uploading, downloading, etc. That demands a lot of energy exhaustion rapidly. So in this concern, we'll study the general architecture of a mobile device and how the energy, and especially in which modules the energy is more consumed and how it is stored, etc. And then of course energy sources, different energy sources I will discuss. And once the energy is taken up from these sources, how they has to be stored and managed, and different design goals. Now to start with, the microcell zoning. This is the most important, the fourth way of enhancing the system capacity. Now what happens in this, as in the figure it shows that we have this architecture. Here each cell is divided into zones. Remember, not picocells or microcells, or not into sectors, but into zones. Now, what are the zones? What additional features the zones have? Let's see. Here, every cell has a single base station, just like the cell splitting part, and the parent frequency is assigned to each zone. So, there is no disturbance in the parent frequency, and each zone is given a directional zone transceiver. So, this property is similar to cell sectoring. So, you can see that the goodness, the advantages of both the cell splitting and cell sectoring are taken into account and put into one, and that becomes our microcell zoning, obviously along with some additional features. Then the directional zone transceivers, the deployment does not depend upon any particular constraints or something. They can have different coverages and they can be put according to the user requirements of that region. Then these directional transceivers do not possess the decision making authority, like whether when the handoff should take place, and if a handoff is detected, then how to resolve it, or whether to resolve it or not at all, etc. So they don't possess this type of decision making capabilities, as earlier it was there in cell splitting, the base stations of splitted cells and transceivers of sectored cells. Okay, so this is a bit different. Now here the zones can overlap to any extent, okay, and this overlap gives enough time for the base station to switch a mobile call between one zone to another. So the switching can be easily done, and this is only because of this overlap. So overlap, the region, the fraction of region that is being overlapped, this can be configured according to what much time is required for switching the calls from one zone to another. Because as you can see in the architecture, that here we have a zone selector, that is it's associated with each of the directional transceiver in the particular zones, and the zone selector is then connected to base station. So base station is not directly involved in these activities of to switch whichever, like transceiver, or is it necessary to not or not. So these decisions are taken by the base station obviously, but with the help of zone selector. Okay, and since there is no handoff, because we are all talking about switching of calls, because the transceivers do not have this power, so there is never a handoff experienced. Okay, there is only switching of calls, that's it. So this is a very big advantage that is there with microcell zoning, that no handoff is experienced, which is very much important for, especially for vehicular communication. Okay, let's see more. What are the important advantages? We have seen the characteristics, the architecture, what it looks like, a zone, how it looks like, etc., how it is managed, etc. Now let's see what are the main advantages. Now this directional antennas, or the directional transceivers that we are talking about, that are deployed in the zones, these are what? These are very low power special category antennas. They are not like the directional antennas that were used in cell sectoring, in the sectors. Okay, so these are even more low power, and they have no restriction in positioning, as we were talking about, that it can be positioned, the height of the antenna is not required to be uniform throughout, it can be positioned anywhere. If there is some region where the deployment is, the need for deployment is very high, there can be multiple zones and there can be a lot of overlapping areas to address the hotspot regions and hotspot time zones, etc. Okay, so here again, what's the second point? It's zones may have identical or different coverage obviously according to the height of the antenna. Okay, and also as a coverage may differ, it need not to be homogeneous throughout. Even the transmission power level, they also can differ. That is, we can combine the microcell zoning and we can relate it with the power control mechanism that we spoke about earlier, that this mechanism is also embedded in zoning concept, that since the coverage is different, the height of the antenna is different, the power level that it takes up is also different. So the service that is provided, that is imparted in each of the zone varies, okay, and it can be decided on the fly as well. That is dynamic deployment of resources, dynamic engagement of resources. Then the zonal overlaps provides ample time for the base station for performing two important tasks: switching the calls of mobile users between different zones, and the second is the zone selector logic can be applied to find the best suitable antenna for the users. Remember that in cell, be it cell splitting or cell sectoring, it is the ultimate power, or we can say that it is the function of base station to decide which antenna is best suited, that is which next potential base station is for our mobile handheld device. So that, and there are different ways again, if you remember that we can use RSS method alone, or RSS with say hysteresis or threshold or both, etc., right, or any prediction method we can apply to find out which base station or which nearby antennas or nearby sectors or zones are able to provide better services than its own antenna, its own coverage. Okay, so the zone overlap is we can see is very important over here. So research problem can be put in this way, that the overlap region, what should be the overlap region, how to optimize this area. This is a very important concern for the network administrators. Now obviously no call is dropped. Why? Because handoff, no handoff, so handoff management issues are all eradicated. So the call never drops. When a call never drops, it means that the quality of service, the quality issue is maintained altogether. So the connectivity and continuity, these are the two important features as far as quality of service is concerned. So at the connection level, so these two issues are well handled by microcell zoning concept. What else? There is ease in maintenance of call continuity for sure, and object mobility. There is no constraint on what rate object should be moving, because mobility is only concerned when there is a chance of handoff. So since here we don't have any handoff issue, so the calls can easily switch between the respective zones. So mobility is not at all of our concern, which is a very again another advantage. So the best application would be on roads or highways where the vehicle speed is too high, and obviously the vehicle speed is high because the roads are less congested. Broad roads, or say the national highways, etc., connecting big cities, over there what we can do, as you can see in the figure also, that the entire highway is divided into N zones, Z1 to Zn, and each of the zone is having small zone antennas. Now these zone antennas can be deployed in a wired or wireless fashion, and they can be connected on with the help of a wired backbone to the base station. Remember that the connectivity between the zone antennas may be wired or wireless, but its connectivity to the base station should be wired. Okay. So here, as we see that the vehicle moves from zone 1 towards zone N, there is no need for handoff, so it smoothly passes, and the zone selector, it applies its logic to switch the services of this particular mobile object from the coverage or the service imparted by zone 1 to zone 2 and likewise to zone N. So this was all about how to increase the number of users, how to improve the quality of service that is being imparted in particular areas, be it zones, sectors, or splitted areas, etc. So now we move on to traffic model. Okay, so traffic model, there is one very basic, we can say that this is a benchmark model, on-off model. This is a very simple model, easy to apply, and it has two states, as you can see in the diagram. The first is silent state and active state. Okay, now silent state means that whenever a mobile device, a multimedia based mobile device is, if it is in the silent state, it means that temporarily it has switched off its transceiving capabilities and it is in its dormant state for temporary period of time. Okay, now it may remain in the silent state for say some probability S. Okay, and it can remain in the active state with some probability, say A. Whenever it is in active state, it means that it has something to transmit, some streaming data it might be involved in. So packets are being produced, they are generated, they can be transmitted or received. So all sort of communication are can be done in the active state. Okay, and obviously there are transitions in between, from silent to active and active to silent, which means that both these states are not permanent, they can be toggled between. Okay, toggle means that none of the states are permanent, they can be switched as per the requirement. Now since we know that the silent state, to be in the silent state the probability is S, so there are only two arrows that are emanating out from the states, which means the probability of both the arrows associated probabilities with both the arrows should sum up to 1. So if the probability associated for being in the silent state is S, it means that the probability, what is the probability that the mobile device moves from silent state to active state will be 1 minus S. Likewise, if we have to move to a silent state, if the device moves to silent state, given that it is already in active state, what is the probability? The probability would be 1 minus A, because A is the probability of being in the active state. Now this entire model is Markov modulated Poisson process. This is the process is known about Markov, because the states and the transitions, this simulates, this resembles the Markov process, and Markov is this property of Poisson distribution. So we can call that on-off traffic model is a MMPP process. Now in this process, the state characteristics, that is what the particular state denotes about, what it refers to. It can be the data rate. Okay, the data, with respect to data rate, it can happen that okay, our mobile device is silent because it's not generating that much of data rate, or it can be above some threshold, so we can say that no, it's active according to what the data rate is. The data rate can be one parameter. Other can be the packet length. Whatever say communication is going on, if it's like transmission of control messages, just to control messages are what? They are the messages that are used for handshaking with other devices, that both the devices are in a particular zone and they are active, so they can now transmit. So how they come to know about this? They can know only when they do a handshaking, that okay, device 1 says I'm alive, device 2 says I'm alive, now let's communicate. So these are small, very small control packets. Okay, so if some control transmission are being going on, then what happens? It's considered to be, if the control message transmission is very less, under some threshold, system threshold, then we can say that it's in the silent state with some probability, or otherwise it is known to be in the active state. Other parameter could be packet type, what type of packet is being transmitted, etc. Now this is, we can see that there are two states, silent and active. There can be even more states as well. So we can split the active state into multiple states. Okay, as we can see that here we have S1, S2 and S3. Out of this, one will be a silent state and the others could be the different levels of activity. So the active state can be divided into some different states. So according to the activity that is being performed, that each active state signifies what? It signifies a particular data rate or any of the network property. Okay. Now the source can be in any one of these states for several active states. Okay. So it has to be in one of the state according to the property of Markov process, and it will generate rate determined by that particular rate. Obviously every state is associated with a particular characteristic. So whenever the node is in one of these states, it has to be abided by the characteristic of the same. Thank you. Welcome back, viewers. We were doing a study on the traffic model. Now let's analyze its performance. Okay. Now we know that the source, that is the mobile multimedia device that is about to transmit some packets, we can designate it as a source node. So a source node has a property to stay either in the active or a silent state with some probability associated with it. Now the source in active state generates, say for example, data rate at some rate lambda bits per second, or it can be packets per second, depends upon the system characteristics. Now if we are known about the data rate, now what we can do is we can find out the probability an, which signifies the length of active period. That is the probability that if we say that the length of the active period is of n time steps, then what is the probability that it is of that particular time step? So this probability can be found out as given in equation 1 as a to the power n, the product of a to the power n and 1 minus a. Okay. Remember, 1 minus a is what? 1 minus a is the probability that now we are switching to the silent state. So it's the collaborated probability of those times when our device was in that particular active state. So we have taken a to the power n and 1 minus a. Okay. And obviously the constraint is there, n should be greater than or equal to 1. We are not concerned about zero values here. Then what? Now we have the probability, so we have to find out the average duration. Average duration can be found out by this formula, Ta is equal to a upon 1 minus a. Similarly, as we have done this for the active period, we can do it for the sleep period. In the sleep or the silent period or dormant period, all these terms are synonymous. Okay, so Sn can be found out in the same manner, and the associated Ts can be computed similarly as in equation 2. Okay. Now once we have all these values with us, the probabilities and the average time, probability, etc., we can find out the average data rate, which we suppose to be lambda a. Now lambda a can be given by this formula, product of lambda and multiplied by the time in active state, the time that the device has already spent being in the active state, and divided by the summation of Ta and Ts. Okay. Obviously since the traffic that we are assuming, it's Markov based, and Markov relies on the Poisson property, so we can say that the traffic is what? It is based on the Poisson distribution. Okay. So assuming Poisson traffic with probability pk, and here k is what? K is the number of packets that arrives in time period t. This can be given by equation 4, and if we check it out, that this is nothing but the Poisson distribution. Okay. So we have all these parameters with us, lambda, lambda a, the time and the value, the probabilities, etc. Now once we have the formulation for all these network parameters, you can just go on and try out this example that is given here. Assume that 64k bits per second voice source. Again, remember that whenever there is a voice source or sound or video, etc., it means that we are dealing with the multimedia traffic. Okay, so say some amount of data is coming from a voice source that is modeled as a on-off traffic source with average duration of active period given, and the average duration of silent period is also given. And the viewers here are to estimate the source parameters, that all these parameters that were there in equation 1 through 4, and the average data rate. So you can just go on trying it out and you can check out your solution. Okay, the average data rate will come out to be 14.77 kbps. Okay. Now let's study about the calling rates. How to analyze the calling rates. Here we have to do some assumptions. First is the new call origination rate is uniformly distributed over the mobile service area. The first important. Second is average number of new originating calls per unit area, say, is taken as lambda a. And now this average call origination rate is completely, it's totally independent of the number of calls in that progress area, in our region of interest. Why is it so? It's because we have large number of users, large number of mobile devices, which means that we are only concerned about the average value. Okay, not that we are interested in checking out the power levels or data rates, etc., for each of the devices. It's not practically feasible. So here we'll always talk about average call origination rate, etc., and these are completely independent of number of calls in the progress area owing to large number of calls, large number of users. Okay. And one more assumption that we make here is the cellular architecture. Obviously, for studying the traffic model, we take up the cellular architecture. We assume that our underlying architecture for supporting multimedia communication is cellular. So all the properties that we studied about cellular architecture will apply on. Next, we can recall that all our homogeneous cells have radius capital R, and this R is what? Basically, it is a maximum distance from the center, that is from the core of the cell where it is geographically stationed, to the cell boundary. Cell boundary means the coverage area of that particular device. So it tends to be somewhat circular, not ideally circular, but we just for the sake of simplicity in our calculation, we take it as a circular coverage region. Now what else? Now once we have all these assumptions with us, we know the constraints, we know the characteristics of underlying architecture and all. Now what we can do is we go on finding out the average new call origination rate of a particular cell. Now we assume that whatever we calculate, it will be uniform throughout for all the cells. So let's calculate for a particular cell. Now this is given by this equation 5, and we can see that the handoffs are executed with average handoff attempt, say lambda RH, and the call ratio can be nothing but the rates that is associated in handoff and the new call origination rate. So it's just the fraction of handoff divided by the new calls. That's it, and we regard this as call ratio. Okay, this is given by equation 6. Now let's move forward. Now here, if new calls are blocked, say we have assumed that new calls are always being blocked due to some system properties or network administration assumptions or restrictions, whatever they have. New calls are always, they are getting blocked by some properties PB. Now this probability is found out on the basis of past records that say for example so far if they have got 1000 new callers and some say 100 calls were always dropped. So the probability will be 100 over 1000, and this way this probability comes up. Okay. So now if new calls are blocked with probabilities say PB and got cleared from the system, okay, then the average rate at which new calls are successfully carried on was a successful rate of passing over these new calls, that these new calls came, they got connected and their services were were totally continued. So what is the probability, what is the rate associated with it? This is given by equation 7. As lambda RC will be lambda R multiplied by 1 minus PB, and PB is what? It's the blocking probability. Similarly, if we have a handoff dropping probability as PH, then we can find out the associated average rate at which the handoff calls are successfully carried is given by equation 8. So you can see that we are concerned about what are the average rates by which the new call, both the new call and the handoff calls are successfully carried on. Okay, so these are the rates, successful rates. And when we find out the ratio of the handoff and new, again we get the actual call ratio. So and if we do a simple calculation ahead, we can see that this actual call ratio is the product of the call ratio that we found in the previous slide in equation 6. This is the same call ratio. So the product of call ratio and the ratio of the probabilities 1 minus PB and 1 minus PH. It's as simple as that. So now we get the actual call ratio, and with this actual call ratio we can determine the quality of a particular network, that given these many number of new callers and some number of say handoff callers, what is the network success rate. So we can find out with the help of this parameter actual call ratio. Now we move ahead. Multi-hop communication. What happens in multi-hop, as this figure shows, that say we have a road and there are vehicles lined up in some manner. So how the communication takes place? There is a Wi-Fi or some other connectivity parameters, some standards are there through which one vehicle can communicate with other, and likewise there is a chain of communication formed altogether dynamically on the fly. Okay. So this is what, so handheld devices, the handheld mobile devices are there with multimedia capabilities, and they have transceiving electronics. For simplicity we have taken it to be homogeneous R. Obviously you can assume it to be some R1, R2, R3 depending upon say all the radius, that is the coverage area is different. So likewise if you want to take, you can assume it in that manner. So then what the multimedia devices with range R, the whatever devices that comes within that range R of a particular device, they are designated as the neighbors. Fine. So if say for example a moving object is considered, so it must have some range R and some coverage area, some area A. Within that area, whatever other devices they lie in, or with obviously instantaneous with time, because since mobility is there, so for a particular time, say it might have some 100 neighbors and it can be some situation where there is no neighbor at all. It might be just going on a highway all alone. There is no other vehicles in the conjunction of its coverage area. So it can happen that way also. So the neighbor set of a particular mobile device is not static. It differs from time to time. Okay, so the mobile devices uses multi-hop communication for transmission of data. obviously how it will communicate whenever it gets to come in contact with neighbors, with different neighbors, and say its source, the source might have a destination somewhere else. So how to reach from the source to destination? The destination might be quite far away. So it is all the intermediate neighbors, or the intermediate nodes that fall in between the progress area. So it is those nodes, the responsibility of those nodes to relay the packet of the source node to the destination. So now what type of estimations we can done with multi-hop communication is, we can find out the expected distance to the next hop, because next hop means the immediate neighbor. There can be so many neighbors. So if the device goes on finding out what is the expected distance reaching to a particular neighbor in its close vicinity, it can find out that which is the best neighbor in that progress direction to which it can forward its packet, so that it can be delivered, it can be thought of or estimated that at least it can be delivered with least amount of delay. Okay. So expected distance to next hop is important. And what else? Expected transmission time incurred, the progress distance, the total distance. So the source node can have some estimation of the time as well, and the delay also, the delay that is incurred in communication. The main goals to minimize delay is how it is achieved, by reducing the number of intermediate hops. But there has to be a trade-off that if the hops are taken too close, then the number of intermediate nodes in that particular progress region would be more. So we don't want to be relayed a packet more number of times. We just want that our packet gets relayed with smallest amount of time period, if efficiently. Okay. So there is a trade-off associated over here. So though we have to reduce the number of intermediate hops, but we have to take care that the number of hops should not increase so much that it incurs a very huge delay. The delay get magnifies. So we have to be careful of that also. Second is optimizing time and distance towards the destination. That is, the progress distance towards the destination has to be identified. It's equally important. And overall, the packets or the communication messages, they has to be routed in a congestion-free, loop-free, and reliable over shortest path. So there are four properties associated with here that how our routing mechanism should be. It should allow the transmission of packets over a congestion free. There should not be frequent collisions, because it will lead to packet loss and ultimately degrade the system quality and output, everything. So it has to be in the first place congestion free and loop free. Loop free means that it should take a proper path. It should not fall into loops, because loops are like a particular say intermediate node is coming over and over again. So it has fallen, we say that the packet transmission has fallen into loops, and as a result of which that packet will never get delivered to its destination in future. So it has to be loop free and reliable, obviously, that we have to be concerned about the link performance of that intermediate path, etc. So it has to be reliable and obviously shortest. It should not be long, because given a particular network, there are so many paths, so many ways there to reach from the source node to destination. But we have to identify the path that conforms to our strategy. That is, it has to be less collision, its link stability has to be more, etc. Okay, and altogether it has to be a shortest path of all also. Now you can see that there are two cases over here, the linear case and non-linear case. In linear case, say S is our source and to reduce the number of hops, what we can do is the source can take its next hop to be C, but since C is outside, or even if it is a little bit closer to N also, we would not prefer choosing C, because at the boundary of any mobile device, what happens, there is a fluctuation in the signal level. So it's not sure that the packet will get delivered successfully. So it's always better to take the node as the next hop, that neighbor as next hop, that completely properly lies within its coverage area. So in this diagram, it's node N, so source will forward its packet to node N and then C, and likewise it will get relayed till the destination node D. And similarly, in the nonlinear case, the nonlinear case looks like as in the figure here. There can be so many nodes, and the node here, the node N, is not linearly lying on the straight line, the straight progress region till the destination node D, but it can somehow get the delay, the associated delay, to be lower if we are taking the node N. So these are the very basic arrangement for the linear and non-linear cases. Okay. Now on the basis of this, let's find out the expected distance to next hop, how to calculate it. The assumptions that are associated with this calculation are that source S has, say, n number of neighbors in the direction of the destination node D, that is in the progress region. And how to find out the distance set, as we know that for every node we have a set of neighbors. So here the set of neighbors are n, that is, say, some S1, S2, S3, some Sn associated with the node S. And with respect to every node, the distance will also be different. So say the distance from source S to some node, say S1, will be distance D1, and likewise D1 to Dn. You have the number of the distance set, and among them it's very easy to find out which node is lying at the maximum distance, and that node will be chosen as the next hop neighbor. Okay, because the one that is with the maximum distance, it means that it's closest to the circumference, to the boundary of the cell coverage, and this will minimize the number of hops. And remember, this is one of our target, one of our challenge associated. Okay, so we have to be concerned on that issue as well. So we take up the maximum distance. Now once we have the maximum distance here, now we will find out the CDF of Dmax, the cumulative distribution function. How to find out? It's nothing but it's a combination or it's a collection of all those values that are less than Dmax. We are bunching up all those values that are less than the maximum value of the distance. Okay. Now then what we are doing, we are multiplying, we are taking the product of all these values, and as you can see in equation 11 that we have got a nice looking simplified version of f of Dmax, and it is Dmax divided by R, and R, remember, it is the radius of the homogeneous cell raised to power n, and n, small n, is what? It is the size of the neighbor set, how many neighbors a particular node S is having. Now we continue with this, and we find out the PDF, the probability distribution or the probability density function of Dmax. Now this can be found out by just differentiating the CDF of that associated function. So it's a very simple calculation over here, and we can see that it is nothing but n by R. There is a number of neighbors divided by R multiplied by Dmax by R raised to n minus 1. Now we can even go a little further and find out we can derive the expected value of Dmax. That is, we are tending to find out what would be a generalized value of Dmax, that is a maximum distance of any neighbor of any given particular node. But just by finding out the expected value, what we are tending to do is we want to find a generalized value of Dmax. So how it is done? Very simple formula. As ED max we have done here, as we are finding out the average value over some range of values. Here the range of value is 0 to R. Why 0 to R? Because we are concerned about the coverage region that is spanning over R. So this is nothing but it's x multiplied by fx dx. So here x is a what? It's d max. So just put in the place of x, you just put d max, and it will give you d max and f of d max, and you will differentiate in terms of d max, that is dt max. So if you do the calculation, you will get it as nr upon n plus 1. This is equation 12. Okay, and this gives the expected distance. Then let's come to expected transmission time. Transmission time is given by the formula in equation 13. It is ETX multiplied by S by L. Here S is what? The size of the packet. It can be bits, bytes, etc. L is the bandwidth of the wireless link. And what is ETX? It denotes the expected number of transmissions. Now, since this is a new parameter ETX, so how ETX can be found out? This is shown in equation 14, and this follows arithmetical geometric series ETX. Okay, so if you just put values from n equal to 1, it says it goes from n equal to 1 to infinity. If you go on putting values n equal to 1 and see what the series, the first term of the series comes out, then the second term, and if you do it, you will find that this is an arithmetical geometric series. So you can apply the summation rule of AG series, and you will find that this is nothing but it's a reciprocation of P. There is 1 by P. And P is what? The probability of successfully delivering a packet. Now once we have the value of ETX, just plug in this value to equation 13, and we get a new equation stating the expected transmission time, that is S divided by LP. This gives the expected transmission time. So you can see that once we have the basic network parameters, we can go on finding out the complicated ones. And these complicated parameters are actually useful for the network administrators or for the users like us to analyze that which network is suitable according to our users or according to our needs. The two more parameters are there, equally important. What is the expected distance, the progress distance? Okay, not just the distance, it's a progress distance given a particular direction of sending our packets or a destination node. This can be done, the formula is given in equation 13. Just plug in the values that we have already derived so far, and you will get the final formulation of the same. Similarly, we can find out the delay associated, which is having a very simplified version as given in equation 14. So these are all 4 important network parameters that helps the users or the network administrators to analyze the performance of its own network. Now let's come to energy harvesting. This is the general architecture of mobile handheld device. We can see that there is a source, it supplies energy, the energy harvesting device. Now this goes to the energy storehouse, or you can say the energy storage, from where the power is properly managed, and it can be used for different activities, the processing or the memory part, or other transceiving electronics like transmitting or receiving, or temporary the toggling that is required between active and sleep state, etc. So this is the architecture, a very simple architecture, so that we can understand that the energy once harvested, where it is stored, and what are the different activities into which this energy that is harvested can be used. Different energy sources that are associated here are the electrical sources, the mechanical sources, and electromagnetic sources. When we are speaking about electrical sources, what is the characteristic? The mobile charging units, these are electrical, they are completely wired charging points. Okay, so obviously whenever a wired concept comes, it means that the maintenance cost is very high and the decay rate is also high. Now the mechanical sources, they are generally generated from walking or typing, and the source is basically the wind or water current, solar energy, etc. generated through vibration as well. Now the electromagnetic sources, these are advantages, they have its own advantages because it's associated. Wireless charging facility is very important. There is no corrosion or there is no decay, you can say that, since we are associated with wireless. And EMF is used to transfer evenly the energy from one object to another, so very much safe for medical implantations, etc. And it has a good, like the technology is very high. But one important drawback is that the rate of charging is very slow. Now the storage devices, once it is generated, how to store it? It can be in the rechargeable batteries or capacitors or supercapacitors according to the need of the applications. And the main design goal that is associated is that we should select low power electronics and choose a particular suitable energy source. And once we have taken the source, energy that is generated should be harvested properly and stored in a proper device, and conversion devices can be deployed as according to the need. And once we are done with all these things, power management is very important. Thank you.
Well, this note, thank you, ma'am. Thank you so very much. And dear friends, if you want to give your feedback or if you have any question to be answered, then you can mail us at info.cc@nic.in. We would be meeting again very soon. Till then, take care. Goodbye. Thank you, ma'am.